all a chemical reaction is whenever you take two compounds or two substances and you combine them in such a way as to create a new substance, or in some cases you take them apart in a certain way to create a new substance. Often what we've been doing so far during the year is we've been working at figuring out how to find certain compounds, and we've looked at that, and now what we're going to be doing is we're going to be saying what happens when we make those compounds, the actual process of that reaction, or we take that compound and break it apart, or even if we say let's put two compounds together and have the ions in them, the cations and the anions switch places. And so these are going to be chemical reactions. In our next lesson after this, we're going to look at different types of chemical reactions. But for right now, all we're really interested in is just looking at writing out chemical reactions. And so the way that we write out a chemical reaction is we use something called a chemical equation. And so we've got one that's sort of on our screen right now. So we have this 2H2 plus O2 gives us 2H2O. And so the basic form of this is that the ones that are over here that are on our that are on the left side, these guys that are right here, are called the reactants. And the ones that are over here that are on the right side, in this case there's only one of them, these are called the products. So we start off with our reactants. Those are the things which react, and we end up with what's left over with our products. Typically the arrow in the middle that shows you the reaction happens is usually pronounced as just yields. So we would say, in this case, 2H2 plus O2 yields 2H2O. And so that would generally be our format here. We've already discussed a little bit about what the subscripts mean in terms of the, in fact, we've done a lot on that, where we've looked at the different molecular formula for different things. And we've also talked briefly about the numbers out front, that this tells you how many H2s we have. And so we have two H2s here. There's no number in front of the O2, so that would just be one O2. And then we have two H2Os, or two waters, that are right here. Now, one thing that allows us to figure out oftentimes these chemical reactions, and this is where these coefficients that are out front come in, is that there is a rule in chemistry called the law of conservation of mass. It says that you have to have the same amount of mass that you start with and what you end with. And that applies to all elements that are within a chemical equation. And so what that means is that if I start with, in this case, 4 hydrogens, I have to end with 4 hydrogens. If I start with 2 oxygens, as in this case, I have to end with 2 oxygens. Now, the little numbers, the subscripts that we've sort of talked about before here, these guys only depend on what the chemical formula is. That's determined by all the things we've done so far this year. The numbers out front, though, these prefixes, these coefficients, though, those can change depending on the way the reaction works. And so some reactions like this one will use twice as much hydrogen as it does oxygen in terms of number of atoms. Others, another different reaction, like if I were going, instead of making water out of this, if I were making hydrogen peroxide, which is H2O2, then there'd be a 1-to-1 ratio of hydrogen to oxygen. And so what we're going to be doing in this unit, or this lesson specifically, in this unit in general, is we're going to be working on balancing these chemical equations. Now, before we go on to that, I want to talk about one special case that we run into. Most elements, because I don't know if you've noticed looking at this, what we've got right here is we have hydrogen right here. We have oxygen right here. Hydrogen is H2, oxygen is O2. We haven't really talked about why that is. We just very, very briefly mentioned it. But effectively what's happening here is that hydrogen and oxygen are elements that are diatomic. Whenever they are by themselves, they form groups of 2. Not necessarily when they're combined with other things, like H2O only has 1 oxygen in it because the oxygen is combined with the hydrogen. But when oxygen is by itself, it's O2. It is diatomic. Same thing is true with hydrogen. The elements which are diatomic are the ones that their names end in Gen or INE. And so if I had something like, for example, fluorine is F, but since it ends in INE, it'll be F2 when it's by itself. If I had iodine is I. When it's by itself, it ends in INE, so it's I2. Nitrogen is N, but when it's by itself, it's N2 because of the fact that it's nitrogen. And so that's the end of that. On to our next bit. All right, so let's suppose that we want to balance this particular chemical equation here. We have to make sure that on either side of the yields arrow, they're the same number of each element. And so let's start off with our hydrogens. Is that to start with, we look and we say that there are 2 hydrogens that are on the left side. So we start off by putting a 2 right here. On the right now, there are 3 hydrogens. So these are not balanced. We have to find some way to get these balanced. The best way to do that is you're basically looking for the least common multiple between the numbers on both sides. So we're looking for the least common multiple between 2 and 3. Least common multiple would be 6. And so that means I need to have 6 hydrogens on either side. Since I have 2 over here, that means I have to put a 3 right here. That gives me 6 hydrogens. And to have a 3 over here, to make that a 6, I have to put a 2 right here. And so by doing that, that is now going to give me, so I now have 6 hydrogens before and 6 hydrogens after. So the hydrogens are balanced. Let's look at nitrogen. Currently, I have a total of 2 nitrogens on the left side, and I have a total of 2 nitrogens on the right side because of that coefficient 2 that's out front. So this equation is now balanced, and so my final result would be 3H2 plus N2 yields 2H3N. So let's take a look at another example on this. So we have Li plus H2SO4 yields Li2SO4 plus H2. So lithium plus sulfuric acid gives lithium sulfate plus hydrogen. So to start off with, let's look at our lithium. We have 1 lithium that's over on the left. We have 2 lithiums on the right. Our first speculation here is let's put a 2 out front here. That gives me 2 lithiums on either side. And so I have 2 lithiums and 2 lithiums. The next one would be hydrogen. I have 2 hydrogens that are over there on the left and 2 that are on the right, which means those are already balanced. We're good there. Now, for our last bits here, for our SO4s, there are 2 ways we can go about doing this. One is that we can break these down into sulfurs and into oxygens. We have 1 sulfur, we have 4 oxygens. But there's another little trick you can do here. If you look at this sulfate, this SO4 does not break up. It's SO4 here and it's SO4 here. And so I can treat that like one whole piece. I can do like an SO4 and an SO4. I can just deal with those on their own. And so that's what I'm going to do here, just sort of to keep things a little bit simple, is that we're going to say there are how many SO4s on the left? There's just 1. There are how many SO4s on the right? There's just 1. And so I mean, I have 1 SO4, 1 SO4. I have, we said, 2 H's on the left, 2 H's on the right. I now have 2 lithiums on the left and 2 lithiums on the right. And so that balances out quite nicely. And so not too much trouble for that one right there. So let's take a look at our next guy here. And so let's try some examples on this. So we have barium hydroxide plus sodium phosphide gives us barium phosphide plus sodium hydroxide. So let's look at the number of bariums we start with here on the left. We have 1 barium on the left. We have 3 bariums on the right. And so to balance this, we're going to put a 3 out front of this barium. That gives me 3 on either side. Now when I do that, that's going to increase my numbers of O's and H's. Let's look at that hydroxide right there. Does the hydroxide split up? No, it's hydroxide on both sides, so that means I can treat this like one group. Right now, over here on the left side, I have 2 hydroxides right there. Times 3 gives me 6, so I need to have a 6 out here. Gives me 6 out there. Now, 6 means I have 6 sodium, 6 NAs, and over on the right I have 6. On the left I only have 3, and so I need to get up to 6, and so I'm going to put a 2 out front. In the process of doing that, though, that gives me 2 P's and 2 P's over here. So it looks like this works out because if you look at it, I have 3 bariums on the left, 3 bariums on the right. I have 6 hydroxides on the left, 6 hydroxides on the right, 6 OHs. I have 6 sodiums on the left and 6 sodiums on the right. I have 2 phosphoruses on the left and 2 phosphorus on the right. So 3 BaOH2 plus 2 Na3P yields Ba3P2 plus 6 NaOH. Nice and balanced. On our next one, we have aluminum chlorate yields aluminum chloride plus oxygen. And so to start this off, I say I have 1 aluminum over on the left, I have 1 aluminum over on the right, those balance. My chlorate, I've got a chlorate here, does it split up? Yes, it does. There is no chlorate over on the right. That means I have to treat these like individual pieces. And so to do that, I say that I have let's look at chlorines first. I have 1 chlorine times 3 gives me 3 chlorines on the left, and on the right I have 3 chlorines, so we're still good. Oxygens, I have 3 oxygens in the chlorate plus times 3 because there are 3 chlorates, gives me a total of 9 oxygens. So 9 on the left, but 2 on the right. Since those don't balance here, I want to look for the least common multiple between these two. Least common multiple between 2 and 9 is 18. And so I'm going to put a 9 over here to give me 18 of these. And then I'm going to put a 2 out here to give me 18 oxygens on the left. But in doing so, I now have 2 aluminums on the left, so I have to put a 2 out here to balance the aluminums. And then from that, I then have a total of 3 chlorines times 2 is 6, and on the left and on the right, I have 2 times 3, which gives me 6. And so 2 ClO33 yields 2 AlC3 plus 9 O2. So onward to our next one here. We have boron nitride plus sulfur yields boron sulfide plus nitrogen gas. So to balance here, let's set this up. We have 1 boron that's over here on the left. We have 2 on the right, so we're going to put a 2 out front. We have 2 nitrogens now on the left, but we already have 2 nitrogens on the right. That's good to go. We have 1 sulfur on the left and 3 sulfurs that are on the right. And so to balance that, we're going to put a 3 in front of that first sulfur. So we get 2Bn plus 3S yields B2S3 plus N2. Now, one quick note here. I want you to notice something. Could I have balanced this by doing something like this, putting a 4 and a 6 and a 2 and a 2? Would that balance? I'd have 4 borons, 4 borons. I'd have 4 nitrogens on the left and 4 nitrogens on the right, 6 sulfurs on the left and 6 sulfurs on the right. That would have technically worked. Whenever you get something like this, is what you want to look at your coefficients, and you want to see, are these coefficients reducible if they were in ratio to each other. A 4 to 6 to 2 to 2 ratio is a reducible ratio. It's a 2 to 3 to 1 to 1 ratio. That's your most reduced form. And so whenever you're writing these out, you don't want to use that reduced form. You want to instead go ahead and use the unreduced, so you don't want to use the unreduced form. You want to use the reduced form in order to get these guys to work. And so if you look at the ones we had before, a 3 to 2 to 1 to 6, that's fully reduced. A 2 to 2 to 9, fully reduced. Can't be reduced anymore. And so that's good to go there. Let's take a look at our last one. C3H8 plus O2 yields CO2 plus H2O. So we start off with carbon. We have 3 carbons on the left. We have 1 carbon on the right. And so we're going to put a 3 out front here. We have 8 hydrogens on the left and 2 on the right. So we put a 4 out here to get that to work. Now oxygens, we have 2 on the left. Now on the right, we have oxygens in 2 different locations. We have O2 times 3 over here gives us 6. Plus 4 times O gives us 4. So that's 6 plus 4 gives us 10. So 10 oxygens on the right, which means we need 10 on the left. And so we put a 5 out front here. And so we look at this. We have a 1 to 5 to 3 to 4 ratio. That's fully reduced. So C3H8 plus 5O2 yields 3 CO2 plus 4 H2O. Now, what happens if we have one of these that you cannot figure out by hand? The method we've been using so far is fairly intuitive. You simply look at how many you have on the left, how many on the right, you try to balance them. But sometimes what can happen, especially if you have elements that are split up, like here, like this oxygen, which appears in both things on both sides, if you have that happening with multiple elements, then it gets really confusing really quickly. And so whenever you have a case like that, there is a mathematical way to go ahead and solve for what the coefficients are. And so let's take a look at that method. Okay, here we have Al4C3 plus H2O yields CH4 plus AlOH3. Now this is one you probably could do on your own using the method we have used before, but let's try using a slightly different method here. And what we're going to do to get this to work is we're going to start off by simply giving the coefficients variable names. And so we're going to call the first one A, the next one B, the next one C, and the last one D, like that. And so we don't know what they are just yet. We're just giving them these variable names. And what we're going to do is we're basically going to see how many aluminums there are, and how many carbons and how many hydrogens and how many oxygens there are with respect to the coefficients. And so if we look at the very first term right up here, we have Al4C3. So if we were asked how many aluminums are in there, there are 4 aluminums in Al4C3, but there are Al4C3s, which means I have a total, if you sort of added everything up, of 4A aluminums. So I put 4A right here. Over on my next one, we have BH2O. There are no aluminums here, so I don't have any that are right there. We have CCH4. There are no aluminums in there, so that's a 0. And then we have DAlOH3. There is one aluminum in AlOH3, and there are D of AlOH3, so that means I just have D of these. And so I start off with a simple equation that 4A plus 0 equals 0 plus D. That's just 4A equals, I just have 4A equals D. And so this is my first equation. For carbons, I have how many to start with? I have AAl4C3. That gives me 3A carbons. There are no carbons here. In the CH4, there's one carbon in CH4, and there's CCH4s. So it gives me just C carbons. No carbons in the last term. So my next equation is that 3A equals C, like that. For my next one, I don't have any hydrogens in the first term. I have 2B hydrogens in the second term. I have 4C hydrogens in the third term. And I have 3D hydrogens in the fourth term. So my next equation is 2B equals 4C plus 3D. Now my last equation, I have no oxygens in the first term. In the second term, I just have B oxygens. In the third term, I have no oxygens. And in the fourth term, I have a total of 3D oxygens. So to work this out, I say I have that B is equal to 3D is my last one. So what I'm going to do here is the next step is basically to substitute these equations in and solve them. If you look at this, I have four variables and 4 equations. If you remember your algebra, you know this is solvable. And so in this case, if I'm looking at this, I'm noticing there are D's in a lot of these. And so because there are D's in a lot of them, I'm going to solve all of these and try to get them in terms of D. And so if I were to write these out, I would say I've got A, B, C, and D I'm trying to figure out. And we're going to solve them in terms of D, and to put them in terms of D, that means D is just D right here. Okay? Now, we know B is 3D. We already know that from what's here. We know that 4A equals D, and so to rearrange that, we'd say A is equal to 1/4 D, and so we say 1/4 D is A. Now, for C, we know that C is equal to 3A, right? Well, A is 1/4 D. And so then C is equal to 3 times 1/4 D. That's a D. 3 times 1/4 D is 3/4 D. So we have 3/4 D. So these are what each of our variables are in terms of D. What you want to do then is the one that you wrote in terms of, in this case D, you're going to pick a value of D that will make all of these coefficients whole numbers. And so we have 1/4 D, 3D, 3/4 D, and D. The proper value for D here would be 4, because if we put 4 in for D, we'll get all whole numbers, which would mean that in this case that A is equal to 1/4 times 4, which is 1. B is equal to 3 times 4, which is 12. C is equal to 3/4 times 4, which is 3. D is, of course, then just equal to 4. And so these are the numbers we're going to put in. And so if we take this out and we're going to erase the numbers that we had in here originally, the letters that we had there, let's go ahead and let's put in our numbers. We had A was 1. A was 1. Whoops. That helps. A was 1. B is 12. C is 3. And D is 4. Let's see if this works. I have 4 aluminums on the left. I have 4 aluminums on the right. I have 3 carbons on the left. I have 3 carbons on the right. I have 24 hydrogens on the left, 12 times 2. I have, 3 hydrogens times 4 is 12 over here, plus 3 hydrogens times 4 is 12 over here. 12 plus 12 is 24. So 24 hydrogens on the left, 24 on the right. I have 12 oxygens on the left, and 3 times 4 is 12 on the right. And so this does balance out. This is how you'd work out this computational method. As you notice, it takes a little bit longer than just working it out the way we have before. But the advantage to this is that if this problem is solvable, this method will always give you a correct answer. If there is one correct solution to it. And so that makes finding solutions a whole lot easier. And so let's take a look at another possibility on this. Another problem will work out in this way, just so you can see how it's worked out. You don't have to do this one very often, but if you need to, then just ding and There we go. And if you do that, then this method will work. So let's take a look at one other possibility on this one. And so we have C6H12O6 plus O2 yields CO2 plus H2O. This is basically the reaction that your body uses when it basically metabolizes sugar. And so C6H12O6 from your biology is sugar here. So what we want to do is, once again, we're going to put some variables for our coefficients, A, B, C, and D in this case. And so we're going to ask how many C's there to start with. Well, we say there are 6A. And there are no C's here, and then how many C's are here? Just C and no C's there. So we say that 6A is equal to C. Our next one for our H's, we have 12A right here, no H's right there, no H's right there, and 2DH's right here because we have H2O times D right there. And so this gives us a total of 12A is equal to 2D, so that's no trouble there. For our next one right here is that what we're going to have is we have a total of 6A oxygens right here plus 2B oxygens right there. Over on our right side, we have a total of 2C oxygens right here, and we have a total of D oxygens right here. And so we have a much more complex equation here. We have 6A plus 2B gives us 2C plus D is our final one here. So we're looking for our values for A, B, C, and D. So we have A equals, B equals, C equals, D equals. Now, to figure this out, we notice, is there anything that shows up in all of them? Well, A shows up in all of them, so let's see if we can write these all out in terms of A. So we can say A equals A to start this off. Do we have any others we can write out in terms of A? Well, C is equal to 6A, no trouble on that one. We know that 12A is equal to 2D. And so if 12A is equal to 2D, then that would mean to solve for D, we just divide both sides by 2 here, right? And so D is equal to 6A. Okay? Now B is our last one. We're going to have to plug in things into our last equation down here to get this to work. We have 6A plus 2B, which we don't know what B is yet, equals 2C. 2C, since C is 6A, is going to be 12A plus D, which is 6A. And so when we do this, we have 18A on the right. We're going to subtract 6A from both sides. And so we end up, when we do that, with 2B is equal to 12A. And so to solve for B here, we're going to divide both sides by 2 again. And so we get that B is equal to 6A again. So in order to get this to work out, what we do is we simply say what value of A would make these all work. The simplest value of A that makes this work is that A is equal to 1. And so that means A is 1 right here. So if we go ahead and erase the ones we started with up here, then we would say that A is 1, that B is going to be 6, C is going to be 6, and D is going to be 6. And so let's double check and make sure this works. On the left, we have 6 carbons. On the right, we have 6 carbons. On the left, we have 12 hydrogens. On the right, we have 12 hydrogens. On the left, we have 6 oxygens. Actually, no, we have 6 oxygens in the first term right here, plus another 12 oxygens in the second term, which gives us a total of 18 oxygens on this side. On the right side, we have 6 times 2 is 12 oxygens here, plus 6 more gives us 18 on the right side. And so that balances out. And that is how you'd go about using the computational method to solve to balance an equation.